So let us recall what we did in the previous lecture. In the previous lecture, we have discussed that a counter examples on continuously differentiable. We have discussed the under the uniform convergence how the differentiability will behave. That means if each fn's are differentiable, we cannot say that the function, a limit function, is differentiable. We have seen the example for that. It is the example which we have seen is mod of x power 1 plus 1 by n. This will tends to the function mod x uniformly. We know that this all of them are differentiable, but mod x is not differentiable in the interval -1 to 1. Even though we cannot interchange the limit and the derivative sign, that means this cannot be done under the uniform convergence. The example for this we have given, it is sine nx upon root n. This is a sequence of function which not satisfying this condition, even though this convergence is uniform. So I have raised the question that under which situation we can do this, or we can do the term by term differentiation. That means when we can interchange these two signs, the derivative sign and the summation sign, when we can do this. So the answer to this questions we'll have into the next theorem, and later on we'll discuss about this statement. So first we'll concentrating on this one and this statement that each fn's are differentiable, and its limit function is also differentiable under certain situations. So let us write that as a theorem. So let fn be a sequence satisfies the following conditions. The first one is fn belongs to D of AB. What is DAB? Is the set of all differentiable function over the open interval AB. So D of AB denotes the set of all differentiable functions. So Fn is belongs to DAB. That means Fn is differentiable function over the open interval AB. Second one, Fn x0, where x0 is a fixed point, is convergent. This will converge for some x0 belongs to AB. That means for some point in AB, this sequence of number actually, because now x0 is a fixed number. So this is a sequence of number, and for one point, at least one point, this sequence of number, that is Fn of x0, is converged. And the third statement is we required is Fn dash, that means the derivative of this Fn converge uniformly on AB. So these are the three conditions is required to be preserves the differentiability under the convergence. Then prove that the first one, each Fn converges uniformly on AB. That means every Fn is converged to F uniformly. And the second situation or second statement we get is limit of n tends to infinity, Fn dash of x is equal to F dash of x. It's ultimately, or which we can write down in the form of limit n tends to infinity d by dx of Fn of x is equal to d by dx of limit of n tends to infinity Fn of x. This is your f of x. So ultimately, this tells you that the limit and the derivative sign can be interchangeable if the sequence of functions satisfies these three conditions. That means each fn's are differentiable. For some point, fn should be convergent, and a derivative of that sequence is uniformly convergent. Let us try to prove this statement and see how we can see. The proof is lengthy, so please be with me till then I can complete the proof. So for the proof, what is given, that are three condition is given, we will use the second condition here. Given that this sequence fn x0 converges for some x0 belongs to AB. So for some point this is convergent. Since this a sequence of functions which are real valued, therefore even though it is convergent, so we can say that it is a Cauchy sequence. So therefore, as the result is every Cauchy sequence is convergent. So I can say that sequence is Cauchy sequence for some fixed x0 belongs to AB. So as per the definition of Cauchy sequence, we can say that given epsilon greater than 0, there exists n0 belongs to n, such that mode of fn x0 minus fm x0 less than epsilon for every n and m greater than or equal to n0. So we call it this inequality as inequality 1, or I can say the statement as statement 1. Also given that the sequence fn dash is converged uniformly on AB. So this will converge uniformly on AB. So as per the same, it is uniformly convergent. By Cauchy's criteria, we can say that fn dash is a Cauchy sequence. So in particular, it is fn dash t is Cauchy sequence for all t belongs to whatever the domain it is, AB is there. So with the same epsilon, we will have some another n0, and you can make it that n0 will be a smaller than n0 and 1. So I can say that exists n1, so n0, such that fm dash of t minus fn dash t is less than epsilon, and I will adjust this epsilon later on for every n and m greater than or equal to n0, and for every t we can have this. I will call this as a statement 2. Now here I am applying the means value theorem on this fn minus fn. So applying mean value theorem to the function fn minus fm, we get, what is the mean value theorem? Let us recall that if you have a function which is continuous over the interval AB to R, if f is continuous, if f is differentiable, then there exists a C which is in AB, such that f dash of C is equal to f of B minus f of A upon B minus A. So here I am applying the mean value theorem for this function. So instead of f, we have fn minus f of t. So I can say that there exists some xi. So you can say fm minus fnt Fm minus Fn x upon t minus x is equal to derivative of this, that is Fm minus Fn dash at xi for some xi belongs to t to x. So for some AB, so instead of A we have t, instead of B we have x. So we'll have this. And if we can simplify this quantity, therefore we can have this is mode of Fmt minus Fnt minus Fmx plus Fnx, that is equal to this t minus x, if I can take on the other side, is into Fm minus Fn xi. Now this is less than or equal to t minus x. What is this? As per the statement number 2, that means Fn dash t minus Fn dash t is less than epsilon. So using that, we can say that this is less than epsilon upon some quantity. It is, the statement 2 said it is epsilon, but what I have told you that I can adjust this epsilon later on, and here the time to adjust that. Since this is t minus x and t and x both belongs to AB, so I can say the mode of t minus x is less than or equal to mode of b minus a. So if I want that this is less than epsilon by 2, then this has to be 2 times b minus a. Then t minus x, according to that, it is less, t minus x upon b minus a is less than or equal to 1. So that's why this is less than epsilon by 2. So I have adjusted my epsilon. Here it is epsilon upon 2 into b minus a. This is because of statement number 2. This step. And this one due to this. Now, the first objective is to prove that Fn is uniformly convergent. That is the first statement we have to prove. That is, Fn is converged uniformly. So actually we have done this work is to prove that one. Now for any x and t belongs to AB and m and n greater than or equal to n0, we'll start with mode of Fnx minus Fmx. So we'll add and subtract some terms here. So it is Fnx minus Fmx is already there. So I will add that Fnx 0 and subtract Fnx 0. So I have adding this term, and also I am subtracting one more term here, that is f n x 0, and adding f n x 0, and the last term is minus f m x 0 is already there, x is already there. So actually I have added and subtracted two terms here. The one is fm x 0 and fn x 0. Now let us adjust some terms by triangle inequality. So this is less than or equal to, I can say it is mode of Fnx minus Fmx. That is this term. Sorry. First we have to use the first equation number 1. So in the equation 1 we have Fnx0 minus Fmx0. So I may rewrite this one as Fn x0. So I can write down this is the first Fn x0 and Fm x0. So that two terms I have written first, and the rest terms is Fn x minus Fm x, which is here. Then it is plus Fn x0 minus Fm x0, which we have the equation number 2 that you can see. But in this we have done that for any x and for any t, this is less than epsilon by 2. So I can say this is equation number 3. And this is less than epsilon by 2 from equation number 1, that you can observe that it's loading, so please. So here I am adjusting this epsilon as epsilon by 2. Due to this, you can say that it is Fn x0 minus Fm x0 is less than epsilon by 2 for every nm for fix n0, and plus for the statement number 3 that we have here, that is this, that is also less than epsilon by 2, and that is equal to epsilon for every nm greater than or equal to n0 and for every x belongs to AB. So it proves that the Fn x is a Cauchy sequence for all x belongs to AB. Therefore, by Cauchy's criteria, Fn converges uniformly. So that proves the statement, first statement. Now we have to prove the second statement. It says that the limit and the derivative is interchangeable. So let us consider, as the limit function is now exist, let us consider the limit of this Fnx is the function fx for every x belongs to AB. So for every x, let us assume this is the things we have. Now ultimately what I have to supposed to do is to take the derivative, that is d by dx of Fn of x, which is nothing but the limit t tends to x, Fnx minus Fn t upon, or t minus x, that is t minus x. So ultimately I have to deal with this limit t tends to x. If I want to prove that it is for any point t, I have to deal with this one. So now let us take this fix for fix any point x in A. Let us define this function which we have denoted here, that is phi n t, fn t minus fn x upon t minus x, as phi n t, that is fn t minus fn x upon t minus x. And phi of t I may define as f of t minus f of x upon t minus x for all t belongs to AB. We may assume this is a function. So ultimate our goal is to prove that phi n of t is tends to phi of t. As if I take the limit of this limit of t tends to x, phi n of t, that means limit of this function, that is limit t tends to x, fn t minus fn x upon t minus x. This is nothing but the fn dash t, fn dash x. This is the things we have. So ultimate goal is to prove this fn t is tend to fn x as n tends to infinity. So now let us see what is that difference, that is what is phi n of t minus phi n of t. Our objective is this will be less than epsilon. But this is what we can have as per the fn t minus fn x upon t minus x minus, sorry, fm, we can talk fn t minus fmx upon t minus x. So this is, we have t minus x is LCM. In the numerator we'll have, it is fn t minus fn x minus fn t minus fm minus plus fmx. And using the statement 3, that is regarding the fourth term, that is fn t, fmx, fnx is less than epsilon by 2. So as per that, this will be less than epsilon by 2 into b minus a, that we have adjust for this 1 upon t minus x. So as per this, and I will call this as a statement number 4, and this is true for every m and n greater than or equal to m0 and every t is belongs to AB. Therefore, what we can say is phi n of t is a Cauchy sequence for all t belongs to AB, and which tells you by Cauchy's criteria that phi n is a convergent uniformly on AB. Now, ultimate goal, or here what is the phi n is convergent, the question is where it is convergent. Since each fn converges to f uniformly, and what is your phi n? Phi n is fn t minus fmx upon t minus x. So this f is converged to, fn is converged to f. So this is f of t, this will be fn of t upon t minus x. So since fn converges to f as n tends to infinity, phi n of t converges to phi of t uniformly for as n tends to infinity for all t belongs to AB, where t is not equal to x. Our objective is to prove this limit will be f dash of t. So let us consider limit n tends to infinity fn dash of t equal to g of t. What is our claim? Our claim is to prove this g of t is same as f of t. This is our objective. And since the limit of fn, limit of this phi n is equal to phi of t, since limit of phi n of t as n tends to infinity is phi of t. By the definition of limit, we can say for given epsilon greater than 0, there exists n0. If we can say different name, no problem, you can use the different name here because ultimately it is some constant such that phi n t minus phi of t is less than epsilon. I need to adjust this epsilon, but I mean tell you this is epsilon by 3, which I can adjust later on, but I know what is the situation is, so that's why I may write it is epsilon by 3 for every n greater than or equal to n0. And we also have this t tends to x. Phi n of t is equal to fn dash of x, which we already have done earlier. That is, what is phi n of t as t tends to x? We have proved that is a derivative of fn x. So due to this is fn dash of x. And as per the definition of the limit here also, for given epsilon greater than 0, epsilon is work is the same. We can have some delta greater than 0 such that t minus x less than delta implies phi n t minus fn dash x less than epsilon by 3. I may call it this is as statement number 6. This may be 5. You may call. And the last one that we also have a limit of fn dash t equal to, we have assumed g of t as n tends to infinity. So for that there exists n1 greater than or belongs to n, such that fn dash t minus g of t is less than epsilon by 3 for every n greater than or equal to n1 and for every t belongs to AB. Now ultimate goal is to prove this g of t is same as f dash of t, but f dash of t is nothing but the phi of t as t tends to. So it is ultimately prove that limit of t tends to x, phi of t. If I want to prove this one, then I have to see what is the difference between phi of t and g of t. So that we can do. So now consider mode of phi of t minus g of t, g of x, and adding and subtracting certain terms here, that is phi of t. If I subtract this phi n of t and add this phi n of t and then subtract fn dash of x, add fn dash of x, and the minus g of x is already there. So by triangle inequality, which is we can write down this is this quantity plus phi n dash of t minus fn dash of x plus fn dash of x minus g of x, and this will be less than epsilon by 3 due to the statement number 5, 6, and if I call this is as a 7. So this is less than epsilon by 3 plus epsilon by 3 plus epsilon by 3 for any n which is greater than or equal to maximum of n0 and n1, because both statement is true for one statement, that is the statement number 5 is true for n0 and the statement number 7 is true for n1, and the statement 6 is true for t minus x is less than delta. So this is less than epsilon, I can say it is equal to epsilon. So I can say that for this value of n, limit of phi of t is equal to g of x as t tends to x, which is exactly f dash of x. And hence, we can say that f dash of x is equal to g of x, and hence g of x is nothing but the limit of n tends to infinity fn dash of x. So which completes the proof of that limit and integration is interchangeable. So you require three conditions to do this. The first one is each fn should be differentiable. Second statement, for some point fn has to be convergence, and the derivative sequence of derivatives is uniformly convergent. These three conditions are required to be have a term by term differentiation. So for that we can have the next result, which is known as a term by term differentiation. So this statement will write in this fashion, that is, if fn of x0 is equal to summation n running from 0 to infinity fn x0, that means for some point x0, for some x0 is in AB. The second statement I required is the summation n running from 0 to infinity fn dash x is uniformly convergent. And obviously this each fn's should be differentiable. That is the first situation should be required. And then we can say that fx is equal to summation n running from 0 to infinity fn x converge uniformly, and a d by dx of f of x, which is f dash of x, which will be summation n running from 0 to infinity fn dash of x. So ultimately, what is the statement says is this: a d by dx of summation n running from 0 to infinity fn of x is equal to summation n running from 0 to infinity d by dx of fn of x. So ultimately this statement says that the summation and the integration is interchangeable. So this is the statement for the term by term differentiation. The proof is very easy if you use the previous results for the sequence. As the convergence of series depends on the convergence of sequence, you consider the partial sum, and each partial sum, since this first situation is there, that is fx, so partial sum of this one is convergent. So I can say that, let us consider, if I want to prove this, consider Sn x is the sum of first n term fkx. So as fx0 is equal to summation n running from 0 to infinity fn x0 for some x0 is in AB, I can say that this Sn x0 is converged to some function, that is here is exactly fx0 for some x0 belongs to AB. So the first condition is satisfied. The second condition is each Sn is differentiable. Since Fk is differentiable and is a partial sum, we know that the sum of two differentiable function is differentiable. So as per that argument, Sn is differentiable. So we note that the sequence Sn is differentiable on open interval AB. So that condition is also satisfied. Now the third condition we have to check for it is the derivative sequence of this will be uniformly convergent, and that is there due to the statement it is given that a summation n running from 0 to infinity Fn dash x is uniformly convergent, which is exactly the partial derivative or partial sum of this, a derivative sum or derivative of this one. So as Sn dash of x is equal to summation n running from 0 to infinity, summation k running from 0 to n, Fn dash x for every x is in AB, and summation Fn dash x n running from 0 to infinity is uniformly convergent. This, the sequence Sn dash, that is the derivative sequence, is uniformly convergent. So ultimately what we can say by previous result is a limit function, that is the limit of this, is uniformly convergent. That is, we can say that therefore limit of n tends to infinity Sn dash x is equal to f dash of x. But what is this? This one is exactly the things which we required, that is summation k running from 0 to n Fn dash x as limit n tends to infinity, and on this side it is d by dx of summation n running from 0 to infinity Fn x. And if you can see that this is, if you take limit n here, then this is summation Fn dash x, that is d by dx of that. That means interchanging of summation and the integration sign is possible if the series is satisfying three conditions. So this will gives you proof regarding the term by term differentiation is possible under that three conditions. So if you have any questions, you can ask.